Okay, so the title for this lecture is called limit point compactness, which is another formulation of compactness. Okay, so the definition is that, okay, given any space, the space is said to be limit point compact if for any subset that is an infinite set, so any infinite subset has a limit point, then we say it's limit point compact. And the theorem states that compactness implies limit point compactness. So we prove it by contrapositive. So we show that A has no limit point implies A is finite. Okay, so this is the contrapositive. So suppose A has no limit points, then A is closed. Okay, remember this. Now for each element A, there's a neighborhood U of A such that it intersects A and only A itself because it has no limit point, right? Which means that we run through all the UAs, and also the open set X minus A is an open cover of X. So as X is compact and X minus A and A are disjoint, so sum of them covers A, right? A is equal to this, and A is contained in this, right? So we have A is equal to A intersect this, and from here we use the distributive law, which is equal to this, and each of them intersects A with only one element. So A is really a finite set. Okay? I mean, in my opinion, this is the proof from the textbook, but in my opinion, well, because A is closed and X is compact, so A is compact, right? A is compact. Closed subsets of compact space is compact, yes. So the neighborhood UA such that, so this is neighborhood of UA, so this is open set in X, open in X. And because A is compact and we have this is the open cover of A, right? Not open cover, like covering of A with open sets in X, right? So finally of UA covers A, right? Again, we get this. So basically, this leads to the fact that A is finite. And here's a remark. Limit point compactness does not imply compactness. So here's an example. For Y is equal to AB, we'll give the topology on Y, right? The trivial topology. And we give X the product space, which is in integers, positive integers multiplied by Y, get the product space. It is a limit point compact because for any subset that is not empty, it has a limit point. So for any non-empty set, it has a limit point. Why? Because say for example 1A is in A, right? Then 1B is the limit point. Why? Because for any neighborhood of 1B, right? Any neighborhood of 1B in here, a neighborhood in open set contains it, it must be something like M times Y, right? Because the topology on Y is only these two sets. So it must be Y, right? It must be something M times Y. For some M open in this, right? And 1 is inside M, right? Because 1B is in something like this, right? Right? So 1B and 1A, they're both in this. Because 1 is in M. So 1B and 1A are both in this. So we're done, right? Because 1B is 1A is in like neighborhood, right? 1A is in A, and 1A is also in this. And if we just delete this, right, we still have 1A in the neighborhood. But the open cover of N cross Y has no finite subcollection to cover as X, so it's not compact. Okay? So this is just some remarks. But in terms of metrizable spaces, okay? So first, given a space, given a sequence, for any increasing sequence of indices, right, have a subsequence. So the subsequence must be that the indices must be an increasing sequence in plus. And we say X is sequentially compact if every subsequence has a converging subsequence. Okay, so this is the Bolzano-Weierstrass property, right? Okay, so we have this is not true in general, but if X is metrizable, then they're all equivalent. Compact, limit point compact, sequentially compact, blah blah blah. They're equivalent if X is metrizable. And this is the only theorem that I'm gonna do proof for this lecture. It is an important one. And metrizable spaces. Okay? So 1 implies 2, we just did it. Right? Compact implies limit point compact. Now we show 2 implies 3. Limit point compact implies sequentially compact. If it's limit point compact, given a sequence, we define A as the range of the sequence. So if it's finite, then we're done, right? Because if A is finite, then there is a point such that X is equal to Xn for infinitely many n, so it has a converging subsequence. If A is infinite, then it has a limit point. It's a limit point compact, right? If it has a limit point, we can pick n1 such that Xn1 is in the one ball generated by X. It's a limit point, this is possible. And now, inductively, suppose I minus 1 is given, right? Since this ball, right, intersects A is infinite set. So we can pick Ni such that, well, we can always pick one that is in here, right? Since this is non-empty, right, we can always pick a xni that is in those, but since it is infinite, we can require this n1, ni is larger than the given ni minus 1. Okay, this is by the infinite because of this, and this we just really can choose any point and A, we call it xni, right? Some any xni here, but we can make this requirement because it's infinite. So now we see that this xni converges to x and is a subsequence of x. So it has a converging subsequence. Okay? 3n plus 1. 3n plus 1 is pretty difficult. So the first step, we show that the Lebesgue lemma holds for x. That is, we have this statement holds for x. For any open cover, there's a delta such that for any set with diameter less than delta is contained in exactly one element from the open cover. So we want to show that this holds for x. Okay? Given that it is sequentially compact. Okay. So first, we assume that no such delta exists and we derive a contradiction. That is, we assume that for each n, there exists a Cn with diameter is less than 1 over n and no elements that contains the Cn. Okay? We're just taking negation of the above statement. Okay? So now we pick xn and cn, right? We pick xn and cn for each cn, so we have a sequence. So we have a sequentially compact, so we have a convergent subsequence, converges to A, and A must be inside some A because it's an open cover, right? For some A and A. So since it is open, so some delta, some epsilon ball, it contains some epsilon ball of it. And now, since we have this, now what we can do is that for I large enough such that we can first make this, okay? 1 over ni less than epsilon over 2. We can make this, and we can also make, because it converges to A, we can also make xni that is in the epsilon delta epsilon over 2 ball around A. So here, this implies Cni must be in the xni, center xni del epsilon over 2 ball, right? Because the diameter of Cni is less than 1 over ni. Less than 1 over ni, and is less than epsilon over 2. And we also have that C and I is in the epsilon ball centered at A by triangle inequality. So here, this and this, but this is also an A. So it contained in some single element, which is a contradiction. Okay. And secondly, we're going to show that for any epsilon, X can cover by finally many epsilon balls. This is like some strong condition. So assume there exists an epsilon that does not work, which means that we can now pick an x1 and x and pick x2 that is not an x1 because it cannot be covered by finally many balls, and then we pick x3 that is not in this and is also not in this, right? Because this is possible because x cannot, this does not work, so x cannot cover by finally many epsilon balls, right? So this is like we can pick this on and on forever, which constructed a sequence, but this sequence has no converging subsequence, right? So this is not even Cauchy. It is not even a Cauchy sequence, right? Wait, I don't think this is the reason. Okay, the precise reason is because first we have that the distance between x n plus 1 and xi is less than equal, greater or equal to delta for 1 for any I from 1 to n, right? So we have then, right? Because we made this construction, so every two thing, their distance is at least epsilon, right? If their distance is at least epsilon, then any epsilon 2 ball contains at most 1 xi. I think it's xi, right? Yeah, xi, right? Any epsilon 2 ball contains at most 1, because if it contains 2, then their distance, right, will be less than epsilon over 2. But we'll assume that this is true. Okay? Okay, so it has no converging subsequence. So now we show that X is compact. So now here it comes. For any, we have this is true, right? The Lebesgue number lemma. We now pick epsilon equals to delta over 3. So we cover X by finitely many epsilon balls. Right? We cover X by finitely many epsilon balls. But each ball has diameter, each ball epsilon is equal to delta over 3, so the diameter must be, right, by triangle inequality, right, the diameter should be like 2 over 3, right, by triangle inequality, right? I'll say diameter is less than equal to, right? Less than equal to, like this is not equal to. Diameter less than equal to over delta over 3, less than delta, right? Anyways, we construct this to get this inequality, right? The diameter is less than delta, so each epsilon ball is contained in a single element, right? But X is covered by finally many of them, so it is covered by finally many of the A. So we're done. Right. So this is the theorem. Remember it: compact, limit point compact, sequentially compact, all equivalent and metrizable spaces. Okay, so I'll see you guys next time.